But this is not something that's new in the literature because it's been done before. For instance, in 2011, Cohen looked at an urban scale processing of emissions. In 2011, 2014, Vinken and Holmes looked at the impact of ship and NOx emissions, which led to a paradox module in geoschem. In 2013, Cameron developed an aircraft plume model to look at the discrepancies between an aircraft plume model and the grid box model. So now that we have described the state of the art, let's look at some model results. So here is just the ozone response to an emission pulse from aircraft emissions at release at 8 a.m. According to our two models. So the blue plot is the box model, and the orange plot is the plume model. So what we clearly see is that the plume or the box model way overestimates the amount of ozone that's being produced in the plume. And we can understand what's happening in the plume when comparing our two models. In the box model, the emissions are being released into a large grid box, which is thus NOx and HOX rich, and thus leading to enhanced ozone production. In the plume model, the emissions are released into a smaller volume, and two phenomena arise. The first phenomenon is an early ozone depletion through endotitration. The second one is the plume becomes HOX emitted, and thus limits the amount of ozone that can be produced in the plume, and thus explaining why the box model tends to have a greater ozone production compared to the plume model. And we did a few parameter studies using this aircraft plume model and comparing our grid box model. But before we go deeper, I just want to define a metric that we're going to use from now is called the emission conversion factor, or ECF, of the species X. And the ECF of the species X is just essentially the perturbation of the species X divided by the amount of noise that's being emitted by our aircraft. And so we did a few parameter sweeps. So for instance, looking at the cross-section of a northern hemisphere at a fixed longitude and sweeping through latitudes and pressures. So the x-axis is just latitude from the equator to the North Pole, and the pressure is the y-axis. And cruising altitudes are around 220 hectopascals. So these are the results on the aircraft plume model, and what's plotted is the ozone emission conversion factor, which can be linked to the ozone production efficiency. So what we see is that our aircraft plume model gives a greater ozone production efficiency towards the equator and towards the ground. And now let me overlay the discrepancies between the grid box model and the plume model. So for instance, if you were to fly an aircraft towards the ground and towards the equator, you see that our aircraft plume model predicts an ozone ECF of roughly 16 or 17, whereas the discrepancies is roughly 20, meaning there's more than 100% error between the two models. And so what we can conclude from this parameter sweep is that the plume model predicts a decreasing ozone production efficiency from the equator to the North Pole, and the grid box model predicts the same trend with a greater magnitude. And additionally, the results of the box model underestimate the fraction of remaining NOx from aircraft emissions at high altitudes, but also overestimate the ones at low altitudes, such as, for instance, ship emissions towards the ground. So the way we want to implement this in geochem is as follows. So we are using ADT flight data to compute gridded NOx emissions, from which we can compute a NOx flow gridded on a 1-by-1 resolution. From this actual NOx flow, we plug that NOx flow into our aircraft plume model, which then computes an effective NOx flow and an effective ozone flow, accounting for plume scale processes. And these effective flows are then remapped into emissions in geochem. And geochem feeds back our atmospheric parameters, which we are using in our aircraft plume model, such as photolysis rates, background conditions, and mixing parameters. And so what my research shows is that the instant dilution of aircraft emissions into coarse grid cells, such as the ones from global chemistry transport models, overestimates ozone production and NOx conversion rates. And the results have been shown to differ by up to 200% after 24 hours at cruising altitudes. And additionally, any macrophysical process, such as control formation, the effect of background aerosols, is neglected in the instant dilution approach, and thus any heterogeneous chemistry that happen on the surface of ice crystals, for instance. And that wraps up my presentation, and with that, I'd be happy to take any questions.
We have time for several questions.
How do you set your mixing parameters in this plume model, and how do they vary depending on the environment?
So we are using the vertical diffusion parameter is defined using the shear and the Brunel frequency from metadata using geochem. The horizontal diffusion parameter is set to 15 meters squared per second. And we are just taking that value from just literature reviews that we've read in the past, and also we account for initial turbulent mixing by just increasing the dilution factor initially in the first few minutes of the plume.
We have time for a couple more.
So in your finding, your conclusion, you mentioned microphysical process can lead to a significant impact on the NOx partition. So how you consider that? You influence dilution, you do not consider that. But for the blue model, do you consider the microphysical effect on the heterogeneous chemistry?
So if I answer your question, you're asking how the microphysical process is affecting the in-plume chemistry?
Right.
Right. So there are heterogeneous reactions that can happen on the surface of ice crystals, such as from in contrails. And these heterogeneous reactions can, for instance, deplete N2O5 and then lead to a greater HNO3 concentration within the plume. And that's how it can affect the NOx partitioning.
So it's only for the country when you have a country form.
Yes.
What about in the case of other countries?
We are the contrail. The discrepancies mainly come from the fact that we neglect the coupling between chemistry and dilution in the instant dilution approach. Whereas in the plume model, we couple those two processes using an operator splitting method. So like we alternate between those two processes.
Thank you very much, Steve.
Right. Thank you.
Our next speaker in this session is Ryan Pound from the University of York.
Hello, everyone. I'm going to be talking about ozone deposition to the ocean and the effects of this on the troposphere. So, to start off, I'm going to quickly go through a summary of ozone in the troposphere and its sources and sinks. So, first of all, we have transport down from the stratosphere. We'll then have chemical production and loss in the troposphere itself. Whilst these are individually very large terms, it's only really the net that we care about these, and this is what we consider. And then finally, we have loss of ozone to the surface. And as well as this, we also have these all balancing out and an extra 326 or whatever teragrams sitting in the troposphere at any one time. But this deposition to the surface term can be broken down. We can consider, in this case, deposition to land and fresh water, where this has been split, and then deposition to the ocean. Now, my work focuses on this ocean term and getting a better understanding of this into the model and refining it using some new work. So, if we're talking about deposition velocities, these are calculated through a series of resistances. We have the resistance, which is termed by meteorology, and this is just the transport of a species down through the troposphere towards the surface. We then have this laminar flow resistance, and this is just the transport of the species through the air that's in contact with the surface. And finally, we have the surface itself, and this is where the physical, chemical, and biological properties of a surface can be incorporated into the deposition velocity. Now, in geochem and in most models, the deposition of ozone to the ocean is treated as a constant for this surface layer. But how well does that perform when compared to observational data? Well, if we take these 5 cruises that all looked at open ocean measurements of ozone deposition to the ocean and compare them on a graph of SST versus their deposition velocity, we can see that there is some form of trend that can be seen in this in this plot, which is correlated to temperature and some other surface properties more. And if we put the model on top of this and look at how it performs along these cruise tracks, we can see that actually this constant description of ozone deposition velocity seems to not really capture any of this observational data at all. It's overestimating and in general just not really a sound response for that. So what should it look like instead of being this constant value? Well, if you take a combination of several papers' work, you can start to build up this picture of an ocean where it has this surface microlayer, this very small micrometer scale portion at the surface where ozone reacts chemically with iodide, and this is the loss mechanism. This is the removal mechanism of ozone from the atmosphere. You don't have this turbulent surface layer below that, which again is still a very small layer, but this is driving some mixing from wind speed above the ocean and mixing down iodide from below to above, and you have this mixing term. How can we capture that in a model? Well, if we look at this equation from the astronaut Luhar paper of 2018, you can see that whilst on the surface it's a very complicated lump of math, actually if we start to break it down, we don't see anything. There we go. If we start to break it down, we can incorporate the rate of ozone reacting with iodide in the surface. This is the removal term. We can then also include ozone being diffused into the water. And finally, the physical properties of wind driving some turbulence and the depth of this very small surface microlayer that we saw earlier. So the one last bit of picture we need is this is a way to see the surface of iodide. So for this, I used Thomas's work on predicting surface iodide concentrations. He's got a poster later. You can go check it out there if you have any more questions. So before we looked at it just compared to those cruises, but if we look in a global picture, this is what ozone deposition to the ocean looks like globally. You can see that actually, whilst there is some local changes due to the meteorology terms, actually it's pretty constant everywhere. So if we jump forward to see what the model now does with these changes in, we can see that not only has it been decreased globally, it now has this structure that's been included with minima occurring at the poles, and then as you go through to warmer waters, you can start to see the deposition ramping back up to close to what it was before, but still lower. So it's added all this extra structure. So if we remind ourselves of what the model was doing before, and now look at what it's doing with this new scheme, we can see that actually now the model's definitely starting to capture this temperature dependence of ozone deposition that just wasn't there before. It's the right order of magnitude, and in some cruises performing really well. What does this do to concentrations of ozone in the troposphere? Well, as you can see here, because we've decreased this sink to the ocean term, that globally ozone has been increased at the surface. The most affected area of this is the Southern Ocean, where we can see between a 20 and 30% increase, and this also has some seasonal variation to it as well. If we think of this in terms of altitude as well, we can see that actually this is pretty much limited to the surface, with only really the Southern Ocean managing to reach up, and after about 2 kilometers, the changes really starting to become negligible and background changes. All these changes are well and good, but how do they compare to actual observations? Because if they're not improving the model in any way, then why would we care? So if we look at Macehead to start off with in Ireland, we can see that the base model in blue and new model, including the updated deposition, have around about a 4 to 5 ppb increase throughout the year, with some enhancement locally. This is the same story if we jump over to Trinidad Head in California. However, the model still isn't capturing this region well, but it wasn't in the first place. If we jump down to warmer waters, where this new equation has much less of an effect, because this is much closer to where it was before. We can see here in Cape Verde that whilst there is still a ppb or 2 increase, the model's still performing roughly as it was before and still very close to observations. Finally, we're going to jump down to the Southern Ocean region, where we have here in Ushuaia in Argentina the closest point of observation to this big band of change. You can see that actually now the model's been brought right in line with the observations. And we look at some Antarctic sites. This is the same as well. Before, the model was really underestimating, and now this, in some places, as much as an 8 ppb increase is really elevating the model to much closer where it should be. And this is the same for the other site as well. So finally, we're just going to remind ourselves of this picture that we had at the start, where we have all of these terms collected together for the different sources and sinks of ozone. And now if we add on these changes, we can see where things are going. The sink of ozone to the ocean has been decreased by 90 teragrams a year, which is a non-trivial decrease. There's more change as well, but the other one I want to draw attention to is the increase in the tropospheric ozone burden, which has gone up by 4 teragrams a year. So decreasing this ocean sink has a real impact, and that's where that's going from. Thank you for listening. If there's any questions, I'll happily answer them now.
How temporally representative are the measurements? Do they occur throughout very turbulent conditions, stormy conditions, unable to persist in that environment?
Yeah, so the observations of the deposition velocity, you're saying?
Exactly.
Yeah. So these happened. So these cruises occurred over a period of 3 years in different seasons as well. So although there's not much repeat at one site, it's managed to capture a lot of different wind conditions, different sea surface conditions, and different iodide concentrations in the surface. So it's about as representative as it is, but there's not really many of these measurements out there anyway. So that's sort of what we've got to work with.
I was wondering, see a large sensitivity to your sort of how you characterize the sea surface layer and air sea exchange?
Yeah. So the depth of this surface microlayer, so that term in the equation where that's combined, this is a big lever, and depending on how you do it, so some original work on this, which has been published in a reference with the Ashot-Luhar stuff, they had a very fixed surface microlayer, and this was fine. And then, but if you then increase the iodide, like we have done using Thomas's work, which is seen to be much more representative, this fixed layer was driving way too much loss. So by introducing a variability to this, as it should do, responding to temperature and different wind conditions, this is then being responsive to that. And there's also questions over the sensitivity of iodide rate coefficient with ozone, and this is again another lever that needs to be sort of looked at more experimentally as well.
Follow up more with that later. So thank you, Ryan. And our next speaker is Sean Wang from Harvard.
Hi everyone, I'm Xuan from here at Harvard, and I'm going to talk about our recent development of tropospheric chlorine chemistry in geochem, which can be simplified as this figure. So for those who may be not that familiar with halogens, chlorine is a kind of halogens. Halogens include chlorine, bromine, and iodine in the atmosphere, and they have a large sources from oceans, and they have also have other sources in the continental areas. And chlorine can oxidize methane and other VOCs. Well, iodine is important for some very small particle formation, and bromine is really important for molecular chemistry. And all of the halogens can destroy ozone. So in GeoChem version 12, we implemented a very detailed halogen chemistry, which include the detailed bromine chemistry and detailed iodine chemistry, but not that good chlorine. That is because the most dominated source of chlorine is from the chloride in sea salt. But GeoChem doesn't simulate sea salt at all. Doesn't simulate chloride at all. So to have a good simulation of chlorine chemistry, we need to simulate the chloride first. So to do this, we add 4 new trace species to the model. That's the fine and coarse mode chloride, as well as the alkalinity from the sea salt. So we emit them with the sea salt. After sea salt emissions, the alkalinity will be titrated by acid gases. Then we have the acidic or neutralized aerosols. Then we assume these aerosols can be internally mixed with other SNA. And then we have ammonia, nitrate, and sulfate chloride thermodynamic system. So in this system, the chloride in sea salt can be transferred to gas phase as HCl, and then can be transported further to the continental regions and potentially again to the particle phase. So we also have a lot of other heterogeneous chemistry related to chloride, which can be happening in both aerosol water and cloud droplet. So here we have a simulation of the chloride particle, and then we have a heterogeneous chemistry we will produce a lot of coloring gases here. So what we need to do next is to add photolysis and gas phase chemistry. If you only choose the important one, that's about 100 reactions. Then you got it. That's the coloring chemistry. Okay, so you may also want some other sources, for example, transport from the stratosphere and the organochlorine, as well as from the fire, and that's a biomass burning source of chloride and HCl. So you may be curious, what's the impact of this chemistry? So here I show the influence of the chlorine chemistry on the global oxidants. So chlorine can influence the chemistry by decreased ozone and the decreased NOx. That's through the CRO chemistry. And they can also increase the bromine budget by influence the HOBr, hydrogenous cycling. And this effect can also decrease NOx and ozone. And this influence is larger than the above two cycle. So globally, the chlorine chemistry include the BRO budget by about 85% and decrease NOx, OH, and the ozone by 5, 3, and 7%. And all of this decrease is dominated by increase of bromine. So if you focus on OH here, you find a lot of blue color here, but you also can find something of the red in the continental area. That's an increase of OH due to the CrNO2 chemistry. So we transfer from the global scale to regional. We compare the color simulation of chlorine species to winter campaign, aircraft campaign. So where the black line here show the median value of the HCl and the CrNO2 in the observations, and right line is our model. So basically, model is able to capture both the vertical profile as well as the diagonal variation of the observations. By doing a sensitivity test, we find that CrNO2 chemistry can account for about 6 ppb of afternoon ozone in eastern US. For all of these simulations, we don't add any anthropogenic emissions. So basically, all of the chlorine sources are from sea salt and nitro. And we try to add some anthropogenic chlorine, but that doesn't change the result much. And this is quite consistent to what Jessica talked about yesterday in her box model. So basically, in the United States, chlorine source are from sea salt and nitro. But this is a very different story for China. There are very few observations of chlorine in China, but if you check some number, they are really, really huge. That's definitely associated with anthropogenic emissions. Here we compare emission data sites, by combine a lot of different literature and inventory, which I listed here, and we use these emissions and compare them to different observations. I will only show an example here because I don't have time. Now here show the diurnal variation of HCl and fine mode chloride in Beijing during summer, and basically our model is able to capture the magnitude of observations, and nearly 90%, more than 90% of this chlorine are anthropogenic contribution. So what's the impact of this anthropogenic chlorine in China? So it can give a decreased NOx slightly because the CRO chemistry, but it can increase the OH. That's because of CrNO2 chemistry, and that will lead to an ozone increase by up to 3% at annual average value. But in winter, this effect will be larger as 4 to 5 ppb. And it also can increase the total PM 2.5. That's because in some of the regions, for example, in northeastern China, where we have a lot of ammonia here, we have more chloride, then we put more ammonia from the gas phase to the particle phase and increase the total PM 2.5, concentrations. So for more of this detail of the chemistry, as well as more of a comparison to observations, you will want to check this paper, which published just 1 month ago. And thank you for your attention. I will stop here and take any questions.
So why are the changes in ozone higher in the northern hemisphere than in the southern?
You mean the why are the change of yeah? That's because there are more acid gases in northern hemisphere. Yeah. Sure.
Did you parameterize thiochlorine, and how did you do so?
So I use some like emission actually from literature and put them for like GFAT for burning area. Yeah.
So, sorry. So do you have any idea of how sensitive you are to errors in that inventory, given that we've seen a couple of presentations about problems with GFAT?
Sorry?
Do you have any idea of how sensitive your results would be to errors in that file inventory?
Sorry, I didn't check that. Yeah.
All right.
All right, we got time for one more. Okay, sorry.
So nitric chloride formation is just like a decrease in acid and then with nitrate. So you look at the nitrate too.
The nitrate change from the, so the chlorine nitrate can decrease, NOx and decrease nitrate, but we have more chlorine. So basically this decrease is kind of small comparing to other, like we also, because I didn't show here, is also decrease nitrate because acid displacement, in the aerosol phase. So that effect is much larger.
All right, thank you very much. All right, and our next speaker is Peter Abbott from the University of York.
Hello, this is some work that I've been working on with Matt Evans, where you're looking to use machine learning to improve a tropospheric ozone simulation. Okay, so this is GeoSchem running over London, and you can see there are biases. This is an ozone simulation. So in the spring, we're biased low. In the summer, we're biased high. In September, we're sort of bright sometimes. And so there's biases all over the show. And how do we improve air quality models? So the most common way is we improve the science. So we make a prediction, we then compare that to observation, we then make process level improvements, and then we compare again to the model. And 90% of the talks here will be this process, which obviously is very important, but is slow. It takes a while to improve the model. Another system would be data assimilation. So this is what is used in meteorological models. However, in meteorological models, the underlying equations are essentially solved, and it's more of an initial state problem. With air quality models, it is not so much an initial state problem, but other related biases such as emissions and chemistry. So we were looking at another approach to improve the model, and we looked at machine learning. So essentially, the bias is the observation minus the model. We were looking if we could calculate a function to predict this model bias. And if we can predict that bias, we can then improve the model. So in order to get an observational data set here, we had to compile a very large data set. So this is all EPA, all EMET, all GOR, and all ozosons from 2010 to 2015. We then removed all urban sites, and any sites that appeared within the same time step and the same grid box were averaged into what we were calling meta sites. This is GeoSchem running at 4x5 resolution. This is mainly because of the amount of time we had to run the model for. And we were outputting all tracer concentrations as well as some physical parameters such as temperature and pressure and a few others. The framework for the machine learning that we were using here is XGBoost, which is boosted regression trees. Now, these are based on decision trees, which are a relatively simple concept, which is essentially you're predicting your bias. Imagine the first tree is going to be splitting on temperature followed by pressure, and then it predicts the bias under those conditions. Well, the real power of this system comes from is that it sequentially makes trees, and each tree is trained on the residuals of the previous tree. So essentially, later trees are able to focus on more rare and sort of extreme conditions. This makes it very powerful for this sort of predictive problem. This is a fast and scalable framework. The training set was 2010 to 2015, but we will now use this on 2016 data. So it's not seen any of the data that we're about to test it on. So there's London, and now we have Los Angeles as well. Los Angeles has got a whole different set of biases going on, so it's generally always bias high. and is very muted diurnal. And also Antarctica, which is totally different, kind of steady offset throughout the year. So we'll now apply the machine learning corrector to this data. As you see, we get considerably better prediction. So in London, it's corrected the different times of the year differently. In Los Angeles, it's able to not only correct the bias high, but it's also able to correct the diurnals as well. And in Antarctica, it is able to pick out the general trend of what is going wrong. So if we show this data again on an XY plot, so this is the off-the-shelf geochem model. And then this is with the corrector added on top. So we now have the root mean square error as essentially halved in London. In Los Angeles, nearly a third of the original value, and the normalized mean bias has gone from a 0.46 down to a 0.03. And in Antarctica, we've again substantially reduced the root mean square error. So what we now did is we now passed, this is all of 2016 data. So this is every single ground observation site, and we just tested how the model performed. So if you take all ground data, you will get a root mean square of about 16.2 and a normalized mean bias of 0.29. Using this algorithm, you will end up with half the root mean square error and 2 decimal places, no normalized mean bias. So what we now did is we took all of the ground boxes, regardless of whether we had observations or not, and just pushed it all through the algorithm. And basically, it was able to identify known biases within the model without being told at all. So you see that, obviously, high over America, we do have observations there, but it was obviously able to identify this known bias. In Europe, we have a slight bias. It was able to identify that. And this whole Southern Ocean bias low was all able to be correctly identified by the algorithm. There are obviously extra sites which have no observations, and obviously we'd have to test to see whether they are or are not correctly identifying the biases. One area I can tell you is China. We know that is actually biased low from some other work we've been doing, but this is obviously to do with if a site is very niche and different, is going to have trouble being able to predict that. So basically, in summary, we can predict the ozone bias in the model, and from observations and model output, this substantially improves model performance. We're looking to apply this to other species, such as PM, and where we really think this could be powerful is in air quality forecasting. There are also some extra applications in human and ecosystem exposure, as well as application of science. Just to say, this is a very small amount of what we've actually done on this. So there's a lot of stuff to do with comparing to ATOM and removing sites. So if anyone wants to come and see a massive graphs, you can come and find me at any point. Thank you. Yeah, so we have looked at the feature importance diagnostics. So you get two with this system. You get weights and gains. Gains is really the more useful of the two, as gains is essentially the weight times by the amount of samples that are being split. So essentially, it's the most profound splits. To a chemist, these can often look a bit bizarre. So they might be being used for more of kind of a spatial awareness of the algorithm rather than direct chemistry. You definitely need to use domain knowledge to identify what is going on there. But it is one of the advantages of the technique is that you can kind of make an assumption of what is being corrected.
Which variables are causing more bias?
You can, but the problem here is generally covariance. So obviously, if there's one variable that is particularly unique, it might go much higher up the list relative to how important it actually is, because of a whole set of other variables are actually working together because they're varying together.
Comment on the number of free parameters in your regression tree?
Well, as in the cross-validation parameters?
How many degrees of freedom are you having in your... Obviously, if you include one offset for every time step and every hitbox, you can get perfect size offset.
Yeah, so it was cross-validated using five-fold. So we essentially removed 1/5 of the data for training. We have done studies where we've essentially started trying to break it, essentially. And one of the most exciting things we found is if you remove all of the Western Hemisphere entirely, we still produce 80% of the correction for the United States, well, apart from California for some reason.
So with classical regression tree, you end up having to make some decisions about how many branches you allow and
Yeah,
how thresholds you split on.
It's surprisingly robust. A big advantage with decision trees is the more data you have, the more robust it is. So a big thing we've found is I can actually get it to work a little bit better with about 10 times the runtime. So what it is there's a bit of a compromise. We settled this is very good. It takes about an hour and a half to run. So with regards to the hyperparameters, it is quite robust.
Thank you very much. Our next speaker is Cuban Dine. Please go ahead.
Okay. Hi, everyone. My name is Huibing Dai. I'm the first-year graduate student from NUIST, and my advisor is Professor Hong Liao. Today, I'm going to give a presentation on the co-occurrence of high ozone and PM2.5 concentrations in the Yangtze River Delta region from 2015 to 2018. The current ozone and PM2.5 pollution is severe in China. The 90th percentile of MD8 ozone in the eastern cities of China can reach 140 ppb, and the PM2.5 can reach 240 micrograms per cubic meter. Due to the local emission and high VOC emission in hot summer and pollution transport from the North China Plain, the Yangtze River Delta is experiencing serious pollution. The observational concentration of PM2.5 from 2015 to 2018 in the Yangtze River Delta are decreased, especially in the western cities. The MD8 ozone, on the contrary, increased rapidly, with the highest increase about 41 micrograms per cubic meter. From the monthly trend, the PM2.5 usually high in December and January. The MD8 ozone are more unstable in the monthly trend, with its highest value from April to September. So that leads to our scientific question. First, did high PM2.5 and MD8 ozone occur simultaneously, and how often they co-occurred? Second, what were the meteorology conditions that lead to the co-occurrence of high PM2.5 and MD8 ozone? Our observational data in 25 cities are from National Air Quality Monitoring Network of China, and we use GeoScheme version 1101 with Maritime-Nested Asia simulation from 2015 to 2017. For the later study, we calculated the deviation of MD8 ozone and PM2.5, and its definition are right here. The DC MD8 ozone are greater than 0 indicates that MD8 ozone is higher relative to the average of this month, and our work mainly to focus on the situation when DC MD8 ozone are greater than 0. So to solve our first question, we selected different levels of positive ozone deviation from 0 to 10, 10 to 20, 20 to 30, 30 to 40, and above 40 micrograms per cubic meter. The color bar represents the percentage of days with positive PM2.5 deviation. We can see that with the increase of positive ozone deviation, the percentage of days with positive PM2.5 deviation are also increased. And when the ozone deviation are greater than 40, the percentage of days with positive PM2.5 deviation can reach 91%, which indicates that the PM2.5 deviation are mostly positive with high MD8 ozone deviation. And this slide shows us the number of days in 2015 to 2017 with the co-occurrence of high MD8 ozone and PM2.5. When the threshold of PM2.5 is 35 micrograms per cubic meter, the number of days of the co-occurrence can reach 140. And when the threshold of PM2.5 is 75 micrograms per cubic meter, the number of days of the co-occurrence can reach 34. It's worth noticing that in the eastern cities of the Yangtze River Delta are the most co-polluted with the MD8 ozone and PM2.5. So to solve our second question, this table shows us the this table shows us the IH deviation under different ozone deviation and the PM 2.5 deviation. To compare the co-polluted with the single polluted, we selected when the ozone deviation are greater than 40 and the PM 2.5 deviation are greater than 60. Under this level, the RH absolute value are between 63 to 80%. For comparison, we also selected when the ozone deviation are greater than 40, but PM 2.5 deviation are less than minus 20, and under this level, the RH absolute value are between 45 to 75%. Thus, the higher RH lead to the co-occurrence of PM 2.5 and ozone. Above all, the observation data shows us a co-occurrence of high PM 2.5 and ozone. So, whether geoscape model can reproduce this result. This is a simulated daily MD8 ozone and PM 2.5 for 2015 to 2017. The normalized mean bias for MD8 ozone in the Yangtze River Delta is 6.3, and for PM 2.5 is minus 30.2. Geoscape will perform the day-to-day variation in the Yangtze River Delta, but underestimate the maximum values. The top figure is from observation already shown in the former slide, and the bottom figure is from geoscape model. Compared with the observation, the geoscape model will capture the change of the percentage days with positive PM 2.5 deviation under different positive ozone deviation. As for the number of days of the co-occurrence of high MD8 ozone and PM 2.5, although we adjust the threshold of PM 2.5 by the normalized mean bias, the geoscape model still underestimates compared to the observational. So that is our summary. The co-occurrence of high MD8 ozone and PM 2.5 are most serious in the eastern cities of the Yangtze River Delta with a maximum of 140 days. And the high RH leads to the co-occurrence of high PM 2.5 MD8 ozone. And the model can well capture the trend of the deviation but underestimate the absolute value. Thank you for your attention.
Quick, we're a little bit ahead of schedule, so we have lots of time for good questions.
How much of the is actually done by Can you repeat the question?
Yeah, the question is how much the co-occurrence driven by the PBLH and the emission, we want to say. That's what we want to do next step. We actually now analyze the observational data, and next step we will use the geoscape model to examine the emission of the meteorology to the co-occurrence of the.
So along this line,
Sorry, I can't hear.
Along this line, how many days are because of how the severity
Sorry, I can't understand.
Yeah, you guys, if you looked at the covariation of the wind speed with this.
Wind speed, we already do the wind, the temperature, and the sunlight, and the RH is the most important to this.
So in your second to last slide, not only did they look different, but the spatial distribution looked very different. Can you talk anything about, talk a little bit about what's happening in the western side of your slide?
That's what we want to know. Maybe it's the industry or the economical is very yeah, the eastern city of the Yangtze River Delta are the most economical region, so that's maybe why they are most co-polluted.
Some researchers suggested that ozone is increasing in China in recent years, partly because PM2.5 is decreasing.
Yeah.
Due to the effect of radiation and electrochemistry. How does your work reconcile with that study?
Yeah, in the former slide, from the annual change, from the 2015 to 2018, the PM 2.5 is decreasing and the ozone is increasing. But there are still lots of the co-occurrence of high ozone and PM 2.5. So that's.
Is there an increased health risk to like a larger percentage of population because of the co-occurrence? Do you expect to be impacting a larger number of people because
We don't know that.
I'm sorry, one last question for me. Which emission inventory for China are you using? Which emission inventory?
Mic inventory.
All right, thank you very much.
Thank you. Yeah, Hi, good morning, everyone. I'm William Postal at Harvard. Today, I would like to introduce our written work about the separation of some ozone formation and high aerosol condition. I think this can understand your question about how PM reduction can affect ozone. I think the talk by Professor Chang Zhang yesterday talk, the government have made a huge effort to reduce emission, so we can see a really fast decrease for PM concentration. However, we find the ozone is getting worse, and especially the ozone level is very serious, especially for example, Beijing, for Beijing ozone in recent years, it's the same as the 1990 ozone level in Los Angeles. It's very terrible. So we want to know why ozone has increased so much. First, in this figure, we show that the ozone increase has increased by 1, 2, 3 ppb in this 4 megacity clusters. The increase Beijing, Shanghai, and there's a slight decrease in the south part. Then we want to quantify the emission. We want to quantify the effects from NOx and VOC emission and from the decrease in PM. The left panel shows that all these factors affect on ozone. We find that the pattern is roughly consistent with what we observed, in which we find NOx and VOC emission will increase NOx in the big cities. It's because its region is under VOC limited condition. However, we find the more important factor is from decrease in PM. We also quantify the pathway that the PM can affect ozone. We find the more important factor is from the uptake of HO2. It means that the ozone suppression has to make a very important contribution to recent the ozone trend. Then we want to know, can such ozone suppression by PM be observed? Here we show the scatter plot for the ozone and for PM and ozone. We find the positive correlation in the region where PM is not high. However, when we see the North China Plain, we find the ozone concentration will level off and very high PM concentration. And this also can be captured by our simulation. When the effect of PM are removed, we can find that the ozone will still increase and very high PM. In which we still find the first important factor is from the uptake of HO2, and then this simulation we find the uptake of NOx is still important. Is because our simulation is based on the condition in 2017. NOx had decreased by 20% from 2013 to 2017. It makes ozone more sensitive to NOx in 2017. So those evidence have give us idea that there's a strong separation for ozone by high PM. And then there's another question: is how PM chemistry can affect the ozone production regime? Here we show the major pathway for HOX. We find that the PM the PM chemistry will move the reaction of O2 with OH more important relative to the self reaction of HO2. It means the PM chemistry will make ozone production more will see limited. And we then do another set of simulation to quantify to confirm this. We reduce NOx and we will see emission from 10% to 50%. We find that the PM chemistry will make the response of ozone to NOx of we will see emission more weak is because there's a lower level of HOX. And we find this fact is much larger for NOx. This is because the overall effect from PM chemistry to increase NOx. So as a result, the PM chemistry will make ozone production more will see limited. So let's go back. That in our simulation we based on the recent result from with a campaign for the uptake of NOx and for the uptake of HO2, we use the 0.2 is consistent with the two-field study. But however, this kind of study is so few in China, especially considered the PM chemistry is very complex in China. For example, the high concentration of TMI, high also water and nitrate, chlorine. So we want there is more better constraint for this pathway in the future. Okay, I will still here to take any questions. Thank you.
Could trends in brown carbon play a role in the association with ozone? So with the idea that the reductions in organics are associated with reductions in brown carbon, which increase the efflux?
Okay, because I still studied based on in Beijing field study, they find the black carbon will reduce the fertility in the surface, but other species will increase the fertility in the high level. So there is an offset effect between black carbon and other aerosol.
Sorry, brown carbon, which has a strong UV.
Okay. I don't know about this.
Are your conclusions at all sensitive to uncertainties in what happens to Hono in China, the Hono chemistry and potential heterogeneous chemistry?
No, I didn't consider that in the simulation.
I'm sorry, man. What is the discussion for HO2 update?
Okay, yeah, I think you're asking the product for the uptake of HO2 is for water of H2O2, and for my simulation, the first part we use uptake as water, and in the scatter plot simulation we use the product of H2O2. They're so different, but it don't make any difference for ozone production.
We started off a little ahead of schedule, and we're still ahead of schedule. Yeah, good time progression. Do you have any more on this one? Yes, please.
What is your confidence about the optical detection of the HO2?
Yeah, you're right. And I think for the optic of NOx, there are a lot of study have shown that I think this kind of study has been explored extensively. So I think there is more confidence for the optic of NOx, but for the optic of HO2, there's only few studied in China where the aerosol is very high. But in the US, there is a lot of study, but the aerosol condition is not very high.
So you looked at the mass, PM mass in the model, but the uptake depends on the surface area. You evaluated how good the model is at calculating surface area rather than calculating mass.
I didn't verify this because I don't have the data for the surface area in the site data. Maybe this is a good point. I can take a look. Thank you.
Getting lots of questions, I'm sorry. Can you go one more? Okay, well, I really appreciate it. We'll get a second round of applause. Our next speaker is Shu from Colorado Boulder.
So, hello everyone. My name is Jen Xu. I'm a fifth-year PhD student from CU Boulder. So there are many studies that estimate top-down emissions recently, and most of them uses observations of only one species. So today I'm gonna present on the incorporation of chemical interactions and co-emissions in the 40-bar constraints for top-down emission estimates. I would like to acknowledge my advisor, Professor Devin Henze, and our collaborators. So NOx, SO2, and CO interact through gas phase chemistries. For instance, both SO2 and NO are directly involved in the ozone and oxygen cycle, and all three species react either with OH or with HO2 and affect their concentrations. These chemistries are further complicated by whether it is under NOx limited regime or VOC limited regime. For instance, under high NOx, increase of NOx emissions leads to decrease of ozone and OH concentration, which then further leads to increase of SO2 concentration. Therefore, if we optimize SO2 emissions only using observations of SO2, that neglects all of these chemical interactions and project errors of other species emissions to the one that is being estimated. To further study how these chemical interactions affect top-down emission estimates, we use GeoScam adjoint model, which uses 40-bar approach, and we perform simulation over nested China domain. To simplify the problem, we only use NO2 and SO2 observations. Both are from OMI, and we optimize NOx and SO2 emissions. First, we check the differences in posterior emissions from the joint inversion and single species inversion. In the joint case, we assimilate both NO2 and SO2 observations and optimize NOx and SO2 at the same time, whereas in the single species inversion, we only assimilate NO2 observations to optimize NOx emissions and only assimilate SO2 observations to optimize SO2 emissions. So here in the top panel, the joint posterior SO2 emissions are different from the single species posterior by up to 42%. And for NOx in the bottom panel, these differences go up to 49%. We found actually the joint posterior emissions lead to better posterior simulations when compared with satellite observations. For instance, inside this smaller domain, so inside this black box, initially the GeoScam simulations of SO2 column densities are lower than the OMI observations, and we see larger increases in SO2 emissions in the joint posterior. And then on the right-hand side, when we compare the posterior simulations with OMI observations, we see better match of the joint posterior, showing this red panel compared to the OMI observation than the comparisons using the single species posterior. For NOx, since this is high NOx region, increase of NOx emissions leads to decrease of ozone and OH, which then leads to increase of SO2 concentrations and better matches with OMI SO2 observations. We also evaluate model simulations with surface measurements. As an example, here we are showing the normalized mean bias of surface SO2 concentrations in China. Note here that all the values are negative, and the y-axis ranges from -50 to 0. So the joint posterior, showing blue, has actually small smaller absolute values than the single species posterior in January, February, November, and December. And these are actually the 4 months that OMI SO2 observations has largest uncertainties. So this means that when the satellite observations of the species that we would like to estimate have large errors, incorporation of observations from of another species helps synergistically change ozone and OH concentrations in the model simulation, which then leads to better estimates of the emissions of the species that we are optimizing. And here it is SO2, and we also found similar behavior for NO2 and over other regions like India. Next, I'm gonna switch topic to the incorporation of co-emissions. And the motivation of this comes from the correlated pollutants emissions and their errors from the same sector. For instance, inside the transportation sector, NOx emissions is dominant. And this emission profile is very different from the emission profile from energy sector, where SO2 emissions are dominant. And these ratios between different chemical species can actually serve as an additional constraint in the top-down emission estimates. To do that, we apply sector-based emission scaling factor instead of the traditional species-based one. And we simulate MALPIT CL, OMI NO2, and OMI SO2 observations. So here I'm showing some preliminary results of SO2, NOx, and CO emissions. So our species-based posterior showing green and sector-based posterior showing yellow both have larger magnitude compared to our prior emissions. And at the bottom panel, we're evaluating these emissions according to their sectors. And for NOx emissions, the posterior species-based posterior emissions has the same emission profile following the prior emissions, but we got a new emission profile using these sector-based posterior emissions, and they have larger magnitude than the other 2 emissions. We evaluate these results by comparing posterior model simulations with surface measurements, and we found that the sector-based emissions can change emission in the correct directions when the species-based posterior emissions do not. So to summarize, the joint inversion reduces errors in NOx and SO2 top-down emission estimates through the synergistic changes of OH and ozone concentrations in the model. The joint inversion improves NOx or SO2 emissions at months when the observations have large uncertainties. And for those people who don't have access to GeoScam adjoint model, we also derived a multi-species mass balance approach, which also account for these chemical interactions, leads to better emission estimates, and it is much computationally cheaper than the Fodivar approach. And for these studies, we have a manuscript currently in revision at JGR. For the sector-based inversions, we found larger posterior emissions than the species-based posterior. And we found the posterior emissions can change in the correct directions in this new framework when the species-based inversions do not. With that, I'm happy to take any question.
For OMI SO2, did you try NASA standard product?
So we are using Bureau product in this study, but we have another work that we evaluate both NASA standard product and Bureau product, and we derive top-down emissions, compare them with different measurements and aircraft measurements. So generally, there are some differences, but the magnitude are pretty similar if using these 2 different products.
Can you briefly explain how your multi-species mass balance works?
Yeah, so it's kind of similar to the single species one, but instead of doing the Taylor expansion of the column density with respect to just one species emissions, we do that for both SO2 and NOx emissions, and it can certainly be extended to as many species emissions as possible. So it's like first order Taylor expansion, and then for instance, if we have 2 emissions, we have 2 variables, and then we have NO2 and SO2 observations. So we have 2 equations, and then we can solve them.
So, a couple sort of connected questions on this sector-based scaling. One I think I possibly missed. What is the spatial and temporal resolution which your scaling is calculated? So would you capture sort of errors in the diurnal profile of the sector's emissions? And second, do you separate, say, different emissions indices within a sector? I'm thinking things like coal power versus natural gas power, which would have different SO2 and NO2 ratios.
Yeah, these are good questions. So for the first one, we didn't account for that diurnal variation. So like we only compare model simulation at the overpassing time of the satellite observations. So all of those diurnal profile would follow the one in the prior simulations. And for the second question, we don't have information on that. So those are following the information from the prior. So it's similar to the species-based inversion. We don't have information on which sector is changing emissions more. But for this one, inside each sector, we don't have more detailed information.
So a lot of people have talked about that have been a increasing trend for SO2 emissions over China in like recent years.
Yeah.
And your new approach on new retrieval could still detect such a increasing trend.
Yeah, so we have another study that is looking at the trend of SO2 emissions at global scale, and we have detected a decrease since 2007 in China. But for this presentation, we just focus on like one year and look at how it is different from the bottom-up emissions. We choose 2010 because that is the year we have bottom-up emission inventory.
In the SO2 product, there's a version that has 3 separate layers that are meant to be used for inversions of different types of sectors, whether it be volcanoes or near surface.
Oh yeah.
Did you try using the products that are separated like that, and did you see any differences?
Yeah, so in this, so that is for the NASA standard product. Are you talking about like the PBL product, the average troposphere? Yeah, so yeah, we are using Bureau product in this study, which doesn't have that. Yeah.
All right. One round of applause. So next up is the poster introduction. But before, well, go ahead and start lining up. So before we start that, I do want to just reiterate that the group photo is coming up at 12. So don't go anywhere. It's going to be fun.
Should just get started.
Cheers. All right, hey, I'm Matt Cooper, and today I'm going to sell you 2 projects for the price of 1. We'll start off with the fact that aerosols impact how well satellites can observe NO2. And we've developed a new method to account for this using satellite-observed aerosol properties, which is pretty cool. Secondly, if you have a satellite-observed slant column and you convert it into a vertical column, you need information about the model profile shape. Then compare that vertical column to a model. It's really important that that profile shape is consistent, or else it's really going to mess with your results, and we are going to demonstrate that using the adjoint. So if you've ever compared a satellite model to, or satellite column to a model column, you're going to want to see that. Thanks.
I'm Rachel Silvern from Harvard. The US EPA reports a steady decline in NOx emissions from 2005 to 2017, while satellite observations of tropospheric NO2 columns from OMI show a leveling off after 2009. We use GeoSchem to interpret this emission trend in terms of observable quantities, and we find a large contribution from the NO2 background rather than an error in fuel combustion NOx emissions.
Hello, I'm Thomas from MCAS in York in the UK. Iodine affects atmospheric oxidants and therefore climate change gases and air quality gases. This can be, for instance, tropospheric ozone, which can decrease up to about 9%, This is driven by, key uncertainty in this is iodine emissions, which is driven by sea surface iodide. What we've done here is take a machine learning process to try and decrease these uncertainties, and we've improved the comparisons with observations. I'm also presenting new evidence for increasing atmospheric iodine from the 1950s to present day by threefold. So if you're interested in turning sparse observations into spatial data sets or iodine in the atmosphere, please come to B13.
We now know that the two most commonly formed oxidized mercury species are short-lived against photolysis. So if you want to know what that means for Hg2 speciation and the atmospheric redox cycle of mercury, you can come see my poster. And if you're interested in mercury, I think I'm your only option.
Hi, I'm Jonathan Mock from Harvard. We've implemented the well-characterized but mostly overlooked since the 1980s chemistry of hydroxymethane sulfonate, which is a reaction of formaldehyde with dissolved bisulfite or sulfite. It forms a molecule that can be easily mixed up with sulfate in the measurements. And so we previously showed that a large portion of what was an extreme haze sulfate in China might actually be this molecule. And in geochem, it turns out a lot of areas might have a similar situation where you have HMS might be sulfate in many areas. Thank you.
Hi, I'm Shuting Zhai from UW. So atmospheric acidity has increased since the Industrial Revolution, peaked around 1980s and then decreased ever since due to the air pollution control strategies. And this may have impacts on tropospheric reactive halogens because the largest source of halogens are either acid catalyzed or can only occur under acidic conditions. So what does this mean for the halogens variations over pre-industrial to present day period? And will this impact other oxidants like ozone? If you want to find out, please come to my poster.
Hi, this is Lei Zhu from Harvard. So the idea that we can use geochem CSAL to do research with all purpose is actually not quite right. I mean, geochem by default has no bromine emission from CSAL because otherwise it cannot reproduce observations. So we fix this by introducing some new, bromine activation method, and most importantly, the latest halogen chemistry. And I can guarantee you that this update will influence your favorite molecules, no matter the ozone, VOC, or mercury. So please check it out.
Hi, I'm Pam Wales from GMAO, and I'm working with our composition forecasting system to develop a tropospheric bromine monoxide product from satellite observations. And since the satellites measure total column, we're trying to see if we can get the stratospheric component correct so that we can subtract total minus stratospheric to get the troposphere. And our initial simulations are comparing geochem to GMI to see if we're getting a reasonable amount of bromine and chlorine transported to the stratosphere. Thank you.
Guess we're skipping ahead. My name is Carl Seltzer from Duke. I don't have to convince you all that ozone is difficult to model accurately, and that long-term high-resolution simulations are computationally expensive, and they do require significant time investments. So our technique is to use machine learning and the TOR database of ozone observations to estimate a suite of human health and crop loss metrics over time. And then in this framework, we're able to translate a number of discrete points into coherent and complete spatial maps, estimate the trends in exposure over time, the drivers, and the subsequent impacts.
Hi, I'm Margaret Marvin. I'm a postdoc working with Paul Palmer at the University of Edinburgh, and I've just started a new project that investigates the impacts of VOC emissions in chemistry on PM2.5 over Southeast Asia. I used the nested geochem model via the Amazon cloud, and I will be incorporating a range of remote sensing and ground-based observations to evaluate the model. And so I have some preliminary results that I'd like to show you if you'd like to come by. My poster is number 19, so thanks.
Hi, I'm Sujay Banerjee. I'm a grad student at University of Alaska, Fairbanks. I'm working with Dr. Jinshu Mao. And we are interested in ground validation for satellite formaldehyde column mounts at northern high latitudes. And we've got measurements from 2 ground-based instruments for the summer of 2018. And we've compared it with geoschem simulations and some satellite data for the last summer. And my poster is at B21. I'll be interested to talk more about it.
Hi, my name is Caitlin Confer, and my poster focuses on the implementation of blowing snow into geochem and how that affects Arctic ozone depletion events. And we're using observations recorded by the OBUI network to assess how well the model performs. And so if you want to find out more, come by my poster at B22.
I just want to take a moment to thank all of our speakers again and the poster session. We had a really great session, and I appreciate it.
And thank you to our session chairs for keeping everybody on time. So please let yourself gently be herded just outside this building. My graduate students will be at the training crowd control.